All right. Welcome back to Physics 112. So today is April 15th. So could be the last lecture that will be on the exams. And then on Wednesday and Friday, we will have 2 review sessions for exam 4 on Wednesday. Okay. And then, sorry, on next Monday in a week. And on Wednesday, I could give you, you can be the teacher for a second. Do you want to have a guest lecture or do you want me to lecture on Zoom? So guest lecture is my neighbor. He's an eye surgeon and you don't have to come, but please come because he will, I see him every day. I will feel horrible if no one show up. So that is an option, or I can lecture by Zoom on Wednesday. Which one that you want? Okay, let's do a quick eye clicker then. A is Zoom, B is lecture by an eye surgeon. Okay. So which one that you want? Let me give the live results. So A is I will deliver a lecture on Zoom. B is my neighbor, which is an eye surgeon, will give lecture about optics in medicine, basically. He's an eye surgeon in Phoenix Children. All right, so 5 more seconds. 3, 2, 1. So I take this as 50-50. I prefer him to give a lecture, of course. So you guys will be exposed to new things. But let me coordinate with him. So either I will still give Zoom and he will give lecture on a different day, or he will just give lecture on Wednesday. Any question? So let's start. So today we will talk about human eye and a little bit about interference. And then I want to take a step back. So before exam 3, we learned that Maxwell says that light is a wave. Wave is a perturbance in space. In the case of light, it is an electromagnetic wave. So the perturbance is in electromagnetic and magnetic fields in space. And it propagates at the speed of light, which is c, 3 times 10 to the 8th meter per second. Okay. So the question is right now, if we want to detect, well, first, another thing that we discussed is how to generate electromagnetic field. One is you can accelerate charges, but there are other things that you learn from chemistry. One is from nuclear reaction. You can generate gamma rays. The other one is when a molecule goes from excited state to ground state, it also emits light. And many things that we see in the visible range is due to the return of the atoms from their excited state to ground state. And then one thing that we haven't discussed much is how to detect lights. Lights is an electromagnetic wave. To feel an electric field, we just need a charge. If we want to feel or sense magnetic field, what do we need? What can experience magnetic force? Yeah, moving charge or currents. So if light is important, then nature would evolve a way to detect lights. And unfortunately, we are all born, well, not almost all of us are all born with optical gadget, which is our eyes. And that's the subject of our lecture today. And interference. And another thing is my colleague, Alex Dunn, will give a talk not immediately after class, but an hour after class in the building next door, which is Goldwater. Okay, so this is not a biology class, but eyes look like this. In physics, we simplify it with basically, if this is eyes, an eye, we basically model it as a lens, okay? And there is a sensor here, okay? Which is analogous to any other eyes or even a screen or an iPhone, meaning like an array of detectors. And we can set the principal axis, the optical axis of the lights of the image, okay? So the first question is, if we want to see an image here, is the image real or virtual? I guess A is A, real, B, virtual. If we want to capture the image on the screen or our retina, should the image be real or virtual? Let's spend 15 seconds. A is real, B is virtual. Five more seconds. Oof. Okay. So it's about 50-50. So maybe I should stop. 3 more seconds. 3, 2, 1. Okay, good. So the answer is it has to be real. So that's actually the definition of real image. It's an image that you can capture with any detector. Okay, so that's one. So you don't even need to know lenses. You should be able to answer this question. Another thing is all of our objects that we see are in front of the lens, in front of our eyes. So if using this equation, which is lens or mirror equation, 1 over the object distance plus 1 over image distance equal to 1 over f, then the image is behind the lens, which means based on the definition, S prime or the image distance is positive, and because S prime is positive, then the image is real. So there are multiple ways to approach the problem. Okay. So this is how we see. And then what else there is different between our iPhone and our lens? Well, first, it's a squishy material. Second is in terms of this image. So let me just draw it. Let me annotate the drawing here. This is the object distance. This one is the image distance. Okay. So what is fixed here? The answer is on the slide. Well, it's covered. So our eyeball is fixed. So the image distance S prime is fixed, which is interesting because when we use mirrors and lenses, the image varies depending on the position. So this one is fixed. And the object is the object. It's something that you want to see. So what must change? From this equation, if this one is fixed, you can change the object distance by moving the object. But one thing that can also change in our eyes is the focal length. So our lens, the lenses in our eyes, they are squishy, like gel-like material and clear and somewhat transparent, basically transparent. And based on the position of the objects, it can change the position. Let me load the, we're lucky. So let me load the lecture notes. because I want to show some simulation. And the fastest way is to click the links here. Any questions so far? So this is the first simulation. Our eyes, it has different, right now we are flipped, the object is on the right instead of on the left, but this is the anatomy of the eyes, but in this class we just model eyes as a screen and a lens, and the object, we can vary the object, and if the focal length of the lens is fixed, then you cannot generate a clear image, because right now the image forms in front of the retina. But our eyes has the ability to change. See, can you see this? Oh, sorry. So yeah, so the focal length change, and we use our muscles to change the focal length of our lenses. And then if the image forms at retina, then we can see focus, like nice image. So that's nice. In optics, the name of this type of just like flexible, or there is a term for it. The name is adaptive optics. So even right now, people use adaptive optics to get better images of, let's say, microbiological samples, or people employs adaptive optics to get sharper images of stars. And all of these are bio-inspired. All right. Any question? Okay. And then next, before, okay, so here, let me draw the rays. So first, from one end, if the rays goes from the bottom of the object to the vertex, so this is vertex of the lens and retina, then there is no bending of lights. Similarly, if the light goes from the object to the lens and past the vertex, there is no bending also. Okay. So let's move the object. Sorry, I'm gonna move the object. It is the same object, but it moved behind the previous position. So this is S, I don't know, initial. This one is S after. When you move the object, like when you place an object in front of your eyes and then you move it further, does the object appear smaller or bigger? This is very, very straightforward. Smaller, right? So this angle here, sorry for this angle here, it's too small. Okay. It's smaller than the original angle. So in this lecture, instead of describing the size of object as y is the same here. We use this term, which is some textbooks call it angular size, but there is a general term for it. The term is subtended angle. Okay. This is a mathematical term. Has anyone ever studied subtended angle? So subtended angle is basically if you have two lines, this angle here, they are subtended angle. It's a mathematical concept. And to be more rigorous, it's basically an arc here, but it doesn't matter for now. This angle here is a subtended angle. So when I say subtended angle, instead of a random arc, this arc here is the object or the image. But since it's really difficult to measure the size of the image in your retina, then it will be this angle here, okay? So the angle, and then we can use tangent theta. Okay. Tangent theta here is what? Y. Do you still remember how to do tangent alpha? Like this size here divided by the size that is, the length that is closer. So it's Y divided by what? I'm looking at you. Yeah, I'm looking at you. Divided by, yes, you. With black t-shirt. No, the one in front of you. Yeah, divided by this angle divided by this distance here, which is here. Okay, divided by S. Okay, so and we call this, some textbook call this angular size, but in this lecture we call it subtended angle. Okay. All right. Basically, we have just derived this thing. Oh, one thing is that if you promise me that you don't put your object right here, right? Then theta is small for small theta. And in this case, it's basically theta in radian is much smaller than 1. Then tangent theta is basically close to theta. So instead of writing tangent all the time, we just write theta. But if you want to write tangent theta, you can. Can you see this or no? Okay. So let me rewrite it. So theta is equal to Y divided by S. Any questions so far? So next is we know that we can, the largest the object that we, okay, so we know that if we bring the object closer, we will see the object bigger. But that thing actually, you cannot do that until it reaches 0. Otherwise, I'm not gonna be on the business. I'm making, I do a lot of optics. We build microscopes so you can see virus and cells. Right? If that thing works, then you can just stick cells in front of our eyes, and you can see big cells. And you cannot do that. So there is a minimum distance where we can see the image clearly. The name of that distance is near point. Okay, and this is from your textbook. So near point. Okay, and I assume some of you are about 20 years old. Your near point roughly is 10 centimeter, but there is no exact number. This is just the number that your book uses. And I think in the class we use 25. I don't know why, but the number that many textbooks use is n is equal to 25. Okay, but you actually have a better eyes than that. But don't worry, it will get worse. Okay, and then soon you have to read like this. All right, so and then and then I call it theta 0 or theta 0 max if you want. So if theta is Y divided by S, the smaller the S, the largest the subtended angle. So for the largest image or angular distance that we can see without using any optical gadget or eyeglasses or magnifying lens is Y divided by N. And N here, well, on the exam, I will give you the N. If I forget, then you can use 25 centimeter. Okay. Let's continue. All right. So next, I'm going to show you one thing, one optical device, which is very simple, which is a magnifying lens. So it's really basic. And on Friday, I asked Finn how to find the optical, how to find the focal length. If somebody gives you a lens, how to find the focal point. Let me show you. I have to be off center. So you can move the lens up and down until you focus light. Then this size here, then the length between the surface and the lens is the focal length. Can you see this spot here? It's bigger and smaller. So it's out of focus, and this one is in focus. Okay. So it's not a fancy optical component, but it's a good place to start. So what is the purpose of the purpose to use magnifying lens is so we can read. Even I use optical lens already when I have Zoom. People in my company, they love to make keynote slides using small fonts. I use magnifying lens that way. One is to one, so you can see bigger image. But in terms of physics, in terms of optics, what is the goal of what does a magnifying lens do? Is it on the slide? So you can view magnifying lens as a way to increase theta, right? The size of the image is proportional to the theta. So you cannot change Y. No, I cannot change the size of this marker, but you can change where you position the object. Okay. So the goal of a magnifying lens is the magnifying lens enable you to bring the object closer. And by bringing the object closer, the lens will form an image which is further away, and based on this subtended angle, you can see those images. Okay. So so this is a lens, and without a lens, then the best thing that you can do is bringing it up to 25 centimeter for me. Okay. But with a magnifying lens, you can bring it closer. Okay. And then I'm not gonna repeat what we did last time, but magnifying lens is made of a converging lens. And then the rays that is parallel from the principal axis get deflected and hit the focal plane. And the rays that hit the vertex also doesn't get deflected. And in the end, you form an image at infinity. Any question? I have a question for you. How can we see object at infinity? We're not gonna continue until somebody answers this question. How can we see object at infinity? Any guess? Oh, there are many guess. Matthew. What? Theta is equal to 0. Well, the object when the object is at infinity, the height also increases. The y prime also increases because it's an image. The object height is the same, but the object distance also increases linearly. Yeah, sorry. Yeah, you increase the height proportionally, but how can we see image at infinity? Hannah, do you want to answer, or Holden? I see, sorry. Maybe my question is not clear. No wonder you guys are struggling. It's not because no one pays attention, but the question is badly written. How about you? So I guess the question wasn't that clear. Sorry. Uh, it turns out that infinity here is a mathematical concept. Infinity for our eyes is, I don't know, 100 meter. That thing is infinity enough. Second, all we care, all our brain cares is the subtended angle. Right? So as long as the angle, and then the angle when you move this object and also scale it along the vertical axis, the angle between you put this object at 100 meter and 101 and a million meter is because the object scales with the distance, the angle is relatively the same. So basically, maybe a simpler answer is that infinity here is 100 meter roughly. So, and the angle that we care, is that clear? Or my English fails me again. So the angle here that we care right now is this angle here, okay? So what is that angle? It's y divided by s. I'm not sure what symbol that I use. So theta magnifying lens is basically, the object is the same, but we can bring it closer, and typically we bring the object at the focal plane. So f, so that's the angle. And then the magnification of a magnifying lens is the final theta divided by the magnification without the magnifying lens. So this one is y divided by f divided by y divided by n. So y cancel. So this one is equal to n divided by f. So that's the magnification of a magnifying glass. So one example is if the focal length of this magnifying glass is 2.5 centimeter, then the magnification, if somebody tell you that please use 25 centimeter as the near point, then the magnification is 10. 25 centimeter divided by 2.5. Okay. And the rest of this, you can probably either you learn it by yourself or you skip it. So basically, turns out that what your textbook says is not proper. That's part of teaching physics, is that we don't tell the whole story. It turns out that you can generate bigger magnification if you bring the object a little bit closer, and then you get +1 if you do that. But this is a minor correction. Okay. So for us, probably it's okay. If the object is closer, then our eyes will work harder. But if that's part of your job, if let's say you fix watches, then you may want to operate in a, you may want to see image without using much of your muscle. All right. So next is defects in vision. Basically, it's a subsection in human eyes about eyeglasses. So probably you know this. There are two defects in vision. One is the difficulty to see object at a long distance. There is a term for it. Anyone knows? It's right there. It's myopia or nearsightedness. Okay. I need to be more confident when I pronounce this word. It's myopia. Okay. So this is a condition. Typically, I see many of you are wearing glasses. So what happened is either there is a defect in the lens or the way your spherical eyeballs shape. What happened is, I'm gonna switch to the simulation again. I switch normal. Why it doesn't work? Oh, I switch to near, so this is myopic. Interesting. Sorry. So what happened is in myopic eyes, the object forms in front of the retina. Okay. You can see in that simulation, also on the lecture notes. So how to correct this condition? Do you, if you know, if you have to invent optometry, would you use converging lens? A is converging lens or a diverging lens? So if you have patient with myopic eye condition, how would you fix the problem? So I'm gonna send this to iClicker. Go ahead, Ron. Good. All right, 5 more seconds. 3, 2, 1. Good. So basically all of you answer correctly, 91% of you. Anyone wants to share why, for those of you who answer B, why did you answer B? Somebody with a cap. There are 4 of you. Yeah, you. Yeah, good. I like that. Excellent. Yeah, because if you put converging, so what is your name again? Nathan. So Nathan answered correctly. If you put converging lens, then the image will form even further from the retina. So you need a diverging lens. So for those of you with prescription glasses, the sign of the power of your lenses is positive or negative? Because I think most of you, the ones with glasses in the audience, their eyes are myopic because you guys are young. The sign of your lenses is positive or negative, or you don't care. You just give it to here, take my money. So the sign is negative. The reason why the sign is negative because the lens is diverging. So in terms of F is negative and positive. This is why converging lens, some textbooks call it positive lens. Diverging lens, some textbooks use the term negative lens. Okay. Any question? Now it's the opposite. The other one is hyperopia, which is something you can read, farsightedness. Okay. So basically here, instead of the image forms in front of the retina, the image forms behind the retina. And based on Nathan's argument, we should fix it with a converging lens. So the light will be more focused. Let me show you the simulation. So this hyperopic, so we can, how to fix it? Maybe I need to use different simulation. Okay, so if I write, Yeah, but if I write the simulation, I would add another lens here so you guys can see. But I didn't write the simulation. Okay. Any question? So in terms of numbers, optometrists use different units, and units is always helpful because it's like one example that I often use is X. Right? You don't want to go to price and say like I bought 12X, just too much. You have to do it like what, twice a week? When I was your age 4 years ago, uh, that's how I survived with X. It's easier to say 1 dozen of X. So in terms of the units, there is a concept in optometry which is it's kind of bizarre. The name is power. So this is not energy per unit time. This is not the power of Hariadi concentration like pH. It's 100 centimeter divided by the focal length. And the focal length has to match this unit, right? So let's say if the unit, if focal length is 10 centimeter, then the power of a lens is 100 centimeter divided by 10. Okay. Or some textbook, I think most textbook use 1 meter divided by f. So if you use this formula, then you have to match the units so you can cancel the units. So the unit of power is unitless. Okay. So this is the drawing with a lens, diverging lens for myopic. So I have this question for you. Let's do eye clicker question. I don't think we will have time to do interference. So I may have to do it before the final exam, and it will not be on the exam. Okay, so exam 4 will be even easier for you. Because you cannot do much with optics. The object can either be closer than the focal point further away, right? There is nothing much that I can do. Like flip the object. All right, so the question is an eye clicker question. Okay, and then I forgot to put the options. So it will be short answer. So this is about myopic eyes. The far point of a certain myopic eye is 50 centimeter in front of the eye. So this is how far this person can see. Okay, and this is written in English. So you need to assign the sign, whether it's plus or minus. Okay, it's actually given. There is a translation of the first sentence here, sorry. In the exam, this sentence doesn't exist, okay? So basically, S prime, 50 centimeter in front of the eye, meaning in front of the lens. That means the image distance is minus. So the question is what lens should be used to focus sharply on an object at infinity? And I just need the focal length, not the power. So let's spend enough time. If you need more time, we can do it slowly. I'm looking for F. And you can work with your neighbor. All right, so the math is really simple. So let's spend So 20 more seconds. Excellent. You can either put unit or without unit, that's fine. 10 more seconds. It's a number, not a word. The answer, I give you a hint. It has number in it. Okay. All right. So diverging is good. So 3 more seconds. 2, 1. Good. So diverging is good. It's a good information. That means you get the concept. Let's just show you the answer using my iPad here. So we know that the answer should be minus, okay? And I will grade these answers after the class. So the object far away, we can put like 100-meter, or mathematically we can put infinity. So S for myopic is infinity. And I'm not gonna put that on the equation sheet. And then S prime is given here, and it has to be negative because it's in front of the lens, right? In front of our eyes, and you do simple math. 1 over infinity is basically 0, and 1 over minus of the image distance is equal to 1 over f. So you can just equate f with minus 50 centimeter. Really simple. Let's do one more iClicker question, and then I will say a few words, and then we can end the class. Next is a hyperopic correction, or hyperopic condition, and I'm not gonna say the word. Farsighted. Okay, so for that, I have an iClicker question for you. So let me read the question, and again, I forget to write the options, which in a way is good because it simulates the exam. Not all exams questions will have multiple options. So the near point of a particular hyperopic eye is 100 centimeter in front of the eye. What lens should be used to enable the vision to clearly see an object 25 centimeter in front of the eye? Right? Again, in front of the eye. So the sign, you should decide the sign of this number, whether it should be positive or negative. The question is, what is the focal length of the lens that we should use? Okay, so let me send the problem to iClicker. Please spend time. Don't just answer immediately. How confident are you with assigning the sign? Maybe one way to do it is by looking at this schematic. All right, so basically almost all of you have answered. 5 more seconds. 3, 2, 1. Okay, good. So maybe I should do it a little bit slowly here. So the image distance, so the image or the object is in front of the lens, so it's plus 25 centimeter, right? An object is in front of the eye, which is 25 centimeter. And then the image here is in front of the lens. So that means the object is, the sign is positive or negative? Negative or positive? Negative. So, and then after you do this, then it's a fairly straightforward calculation. So this one is, so basically, this, no ruler here. This is 4 by 100 centimeter. And this is minus 1 divided by plus 100 centimeter. I'm just going to combine them. 4 minus 1, which is equal to 3 divided by 100 equal to 1 over f. So 3 divided by 100, let me just do 3 divided by 100 centimeter equal to 1 over f. Can you see it? No? Then f is equal to 100 divided by 3 centimeter, and the sign is positive. Okay. Any question? So it's really subtle, the difference between myopic, hyperopic, plus, negative, Arman. Because it's in front of the lens. The image is in front of the lens because it's a lens. If the image is in front of the lens, then it's negative. On the exam, we will give you the table, and you should review it. If it's not clear, you should let me know. And I will edit the table. All right, I still have 3 minutes. Unfortunately, we don't have time to do something that is very important, especially in the context of quantum mechanics, which is interference. And I've seen at least one person that benefit a lot from interference. Okay. So interference is basically if you have two waves, and one can be in nature, the other one can be a wave that, let's say, your AirPods add, then you can either have constructive interference or destructive interference. Okay. So basically, at any point, this is the sum between the wave 1 and wave 2. Wave 1 and wave 2, right? If they are shifted by 180 degree, then the sum is nothing. This is the concept behind noise canceling earphone or AirPods, which is something that you shouldn't have. Because when your spouse asks you and you don't respond, you'll be in trouble. So this thing is dangerous, okay? But I hope, by like this 2-minute lecture, you learn the physics behind earphone, which is basically you have sound, let's say from me, and then your AirPods generate wave that is shifted, and the sum between these two waves would cancel the noise. Okay. And this is why for noise canceling earphone, they works best if the noise is periodic, like when you are in an airplane, let's say. But if the noise is, let's say, this lecture, it doesn't work as well. All right. So I guess this is, how many of you will be in the class on Wednesday? Meaning like some of you are planning not to take exam 4. Okay, then I'll see you on Wednesday. All right, see ya.